So we're going to state and prove the second part of the fundamental theorem of calculus. But before we do that, I'd like to get used to a different kind of function expression. So an example of the kinds of functions we'll look at in this part of FTC is given here. So I have a function g of x defined to be the integral from 1 to x of the square root of 1 plus t to the fourth. And this is a problematic notation here, so this should be dt. So the thing I really want to emphasize is that g of x is a function of the upper limit of integration. So it's not a function of t. Often people refer to t in this case as a dummy variable. There could be any variable in there, and importantly, I very much should have had dt, so that should match there. But you can imagine that if we could anti-differentiate this, then we plug in the bounds, t's gone. We have things that just involve x. But what I'd like to do is think a little bit about how x then kind of affects this, and maybe we could try to visualize this. So if I think about, let's sketch here. This function of t. So we're going to have, this would be y equals root 1 plus t to the fourth, and this is with t here. You can imagine that, first of all, we can try to answer a few questions. What is g of 1? Well, g of 1, according to the definition of this function, I replace my red boxes with 1, so we get the integral from 1 to 1 of 1 plus t to the fourth under the square root there. And we have a property that tells us that that's 0 because we're evaluating this integral from a constant to itself. So importantly, what we can see is that didn't involve actually having to think about anti-differentiating or anything like that. We simply were using a property of integration. Now, if I were to plug in a different value of x, then to find g of x explicitly, I would need to be able to integrate. And that's much more complicated. This is not a simple function in the integrand here. But what I can think about is, suppose this is 1. If I had a value of x, then what we can think about is that g of x is essentially giving us the area under this curve between t equals 1 and t equals x. So as I move x around, that would change this right edge of my region. And so the resulting area under the curve would vary as well. And so we can start to think about moving x. Would that increase the area? Would it decrease the area in different parts? So in particular, for fixed values, I could ask, we could say g of x is positive when x is strictly greater than 1, because we're integrating from 1 to a value somewhere to the right, and I know that my integrand is positive. By the same token, I could say that g of x is negative when my x value is smaller than 1, because then you'd be integrating from, say, 1 to 0. If we integrate from right to left, we know that we can flip it if we multiply by a negative. So even though my integrand's positive, that negative multiplier would make the result negative. So that's just an idea about these types of functions. If we think about this next example I have here, I want to make a connection between the integrand and this function we're defining in this manner. Here I'm saying g of x is the integral from 0 to x. And we want to use this piecewise defined integrand to sketch the graph of g of x. So one thing that can be helpful is I sketch the graph of f of t first. And we can think about some points through which g would have to pass. And from there, sketch the resulting graph. So much like we saw before, if x is 0, we know that the integral from 0 to 0 is 0. Now, the other values for this, I can actually take advantage of area. So, for instance, when x is 1, I'm finding the area of this triangle plus this square. and we're going to get 3/2. And then if x is 2, I add on that next triangle and get 2. And we can continue this process. Notice that I have negative area when I get past 2 and between 2 and 4. And then at 6, we end back up at 2. So thinking about this here, what I want to look at is the sketch of this. So if I were to sketch g of x, then this, let's see, we're going to include this. Let's scale it so this is 2. So then we see passes through the origin, and then we jump up to 3/2 and then 2. And let's see, then we go back to 3/2, we go down to 1, 3/2, and 2. So I could connect these. Let's make it kind of smooth. I'm just sketching the graph. What I'd like to point out, though, is the connection between this graph and the one I've sketched above. Let's see if I can zoom out a little bit. In particular, we saw that between 2 and 4, f of t was negative. And notice that between 2 and 4 here, the function was decreasing, the g of x function. And likewise, where I see that my f function is positive, we see that g is an increasing function. So one connection, and this is going to be formalized when we write out this second part of the fundamental theorem, is that this is a similar connection we see between a function and its derivative. And in particular, if we think about the derivative of g being f, because we see where g is increasing, f is positive, and where g is decreasing, f is negative. And it turns out that's true. That's one of the things we're going to see. Again, we have to think about when can we make that assumption, what has to be true about f to begin with. And again, we'll have to be careful with notation. But the purpose of this video is just to get us a little bit more comfortable with this idea of a function defined in this way, that the variable is as part of the limit of integration. And then we can state the second part of the fundamental theorem and go through the proof to see why it's true. And of course, finally, go back and look at some examples where we can directly use that theorem.